During the process of photosynthesis, organelles in the leaf called chloroplasts absorb sunlight. More specifically, the light is absorbed by large pigment protein complexes in the thylakoid membranes of the chloroplasts. One of these large pigment protein complexes is the photosystem II supercomplex of plants. In order to understand the role of the different components in the light harvesting machinery, and to extract useful design principles, we have to study the flow of energy after light capture. To study the energy dynamics, we typically consider subsystems one at a time. Let's focus on the CP29 light harvesting complex that acts as a conduit for energy from the peripheral light harvesting antenna to the core of the photosystem II supercomplex. Like all light harvesting complexes, CP29 consists of pigment molecules and a protein backbone. We will concern ourselves only with chlorophyll pigments that give leaves their green color. Energy transfer dynamics is determined by the system Hamiltonian. The main problem in modeling energy transfer is therefore to determine this Hamiltonian. An accurate and accessible way to find the Hamiltonian of a complex like CP29 is to fit its experimental linear spectra with simulated spectra. If a good simultaneous fit of different spectra can be obtained, the Hamiltonian of the simulation will approximate the true Hamiltonian. In such a fitting procedure, it is crucial that the modeling of spectra should be accurate but also efficient. In this talk, we investigate the accuracy of different methods for simulating linear spectra. A linear spectrum is the Fourier transform of a time-dependent spectral tensor multiplied with a dipole factor matrix. We consider three types of linear absorption type spectra: absorption, linear dichroism, and circular dichroism. Linear dichroism is the difference between the absorption of horizontally and vertically polarized light, and circular dichroism is the difference between the absorption of right and left polarized light. Each spectral technique has its own dipole factor matrix, which can be calculated from the transition dipole moments of pigment molecules, the angle between the transition dipoles and the normal vector of the molecule, and the positions of pigment molecules. The spectral tensor is given by the dipole-dipole correlation function and therefore describes how the polarization in the system changes due to excitation with light. To model this change in polarization, it is necessary to describe two phenomena. The first phenomenon is that dipole-dipole interaction between the transition dipole moments of different pigment molecules may lead to the delocalization of excitation. Such a delocalized superposition state is called an exciton. The second phenomenon that we should describe is this. The pigment molecules are jostled about by thermal vibrations in the protein structure and vibrations within the pigment molecule. A good assumption is that the energy depends quadratically on the nuclear coordinates. Although each vibration is harmonic, the collective motion of the many vibrations in the system causes stochastic fluctuations of the transition energy. It is not possible to find an exact, closed-form expression for the spectral tensor, but we can calculate this tensor nearly exactly through Monte Carlo integration. We perform this integration by considering this stochastic equation, which has the form of a stochastic Schrödinger equation. The absorption due to the unitary dynamics of exciton states is described by the first deterministic part, while the second part of the equation describes the stochastic tugs and pulls on the energies of pigment molecules due to interaction with the many nuclear vibrational modes. We can use stochastic integration and Monte Carlo averaging to calculate the spectral tensor numerically and nearly exactly. Although this numerical approach is virtually exact, it is also extremely slow. It is so slow that it is unfeasible even for the simplest of systems, if vibrations are to be accounted for accurately. To calculate spectra of real complexes, we need to revert to approximate methods. We will discuss 4 approximate methods: the full cumulant expansion method, the coherent time-dependent Redfield method, and 2 methods in which the time-independent standard Redfield and modified Redfield rates are used. Of course, each of these approximate methods can be used to calculate either the absorption, linear dichroism, or circular dichroism spectra. The full cumulant expansion method is significantly less expensive than the exact method, and its spectra is nearly quantitatively correct, as we will discuss in more detail later. I show the applicable expressions in the grey box for those that are familiar with the field, but I will not elaborate on these expressions. The coherent time-dependent Redfield model is the so-called secular version of the full cumulant expansion, which means that it does not account for coherence between exciton states. It is cheaper to calculate, but is also less accurate. The modified Redfield method and the standard Redfield method are fast, but inaccurate. Because of their speed and ease of implementation, the Redfield and modified Redfield methods are often used in literature for the calculation of spectra. The accuracy of the approximate methods can be investigated in more detail by quantitatively comparing the approximate spectra with exact spectra. Such a comparison is shown here as a function of the energy gap and the coupling between pigment molecules for a dimer system. The warmest color represents the best accuracy. The comparison is shown for absorption spectra with perpendicular dipole moments, absorption spectra with parallel dipole moments, circular dichroism spectra, and representative linear dichroism spectra. A few observations are of interest. Firstly, the full cumulant expansion is always the most accurate method, and only for the calculation of circular dichroism spectra is the full cumulant expansion slightly inaccurate. Secondly, the coherent time-dependent Redfield method is the second most accurate method. Since this method is the secular version of the full cumulant expansion, however, the inaccuracies indicate that the secular approximation, which is often made in literature, may be invalid, especially for strong interpigment coupling and for circular dichroism calculations. Thirdly, when the coupling is 0, all of the approximate methods are exact, and the spectra therefore correspond perfectly. This means that cheap methods can be used to calculate spectra exactly for isolated pigments or pigments that are coupled very weakly. We also observe that circular dichroism spectra are least accurately calculated of all the spectra. Finally, we observe that the Redfield and modified Redfield methods perform the worst of all the methods, especially at small energy gaps. These methods are used frequently in literature for the calculation of spectra, and some of these literature calculations may therefore need to be reperformed. It is clear that the accuracy of the approximate methods depends on the spectroscopic technique, and therefore on the dipole factor. The dipole factor is a matrix, and the accuracy of spectra can be represented graphically as a function of the elements of this dipole factor matrix, with the off-diagonal elements on the x-axis and the diagonal elements on the y-axis. The dependence of the accuracy on the dipole factor matrix is complicated, but notice that the absorption dipole factors of CP29, which are represented by the green dots, and the linear dichroism dipole factors of CP29, which are represented by the red dots, lie in the range for which the approximate methods are most accurate, when the coupling between pigment molecules is weak. When the coupling is strong, however, some of the linear dichroism contributions for CP29 differ significantly from exact spectra. In conclusion, linear spectra may be calculated exactly, but such an exact calculation is very expensive. The full cumulant expansion is a very accurate approximate technique that can almost always be used for quantitative calculations. In light harvesting complexes such as CP29, the coherent time-dependent Redfield method may be used for accurate calculation of absorption and linear dichroism spectra, but only when the interpigment coupling is weak. The standard Redfield and modified Redfield methods should not be used, however, when a more accurate approach is available. Thank you for listening.